So today's session's about transformers in general, but we're going to look at two specific transformers, OptionT and either T. And so just to start, I'm going to do a couple of different things at the REPL. But I want to remind everybody of something we talked about in one of the previous sessions. We were talking about the different levels of engagement in the way you go about using these type classes. And I gave one example. There's a certain level of engagement where you're doing it just for the polymorphism, where you just want some useful methods that happen to exist on, I don't know, let's say monad or applicative or whatever. And you know your data type that you're working with concretely, you're working with an option or you're working with a list. And you just want to be able to get the reuse of one of those convenience methods available to you. And that's, one level of engagement is that you're working with concrete types and you just want that reuse. Then I talked about sort of a deeper level of engagement where you start taking advantage of parametricity, you start abstracting over your actual type constructors, so you sort of forget that you're working with an option. You say, just give me an arbitrary type constructor that takes, or that has a monad instance. You start working with that, and I talked a little bit about how that makes your code in some sense more concrete and less abstract, because it really limits what you can actually do in the implementation of a given method. So we're going to see some examples today of maybe that second category or that second type of use where we're going to have to start working with arbitrary type constructors. But anyway, let's get started at the REPL. I'm going to do a couple quick examples of things we've reviewed or we've done in all of the previous weeks. So I have a REPL here. I've imported our structures library, all the instances for the standard library, for list and option and either, and some syntax extensions so we can do things like call our type class methods directly on types. So of course, we had the example where we had list 1, 2, 3, and we voided it out, right? That's just coming from the Functor type class. We're getting the Functor list instance from this import here, and we're getting the extension methods, the fact that we're able to call void directly onto list, from the extension methods from the ops trait. If we had to call it directly through the type class, we could look up the type class this way. Once we've looked up that type class, we can, we could have called the void method on it, passing our parameter in, right? It's all the same thing, just different syntax. So one of the things we talked about was how functors compose. And we saw this, I think, in the first week. We had this example, right, where we were able to take the functor for list and the functor for option and create a new functor for a list of options. Right, so we did an example where we had, we'll just call it x's. We had an example like this with a set of x's, and we can use that composed functor to map over entries in this collection. And remember, because we composed the non-determinism of the list functor with the optionality of the option functor, we can work directly on our integer type here. So for instance, we can just say +1 on each entry, and our composite functor, res3, handled both applying that to every element in the list, as well as applying it only to the sums and skipping the nones. So we saw this in a bunch of other cases too. Almost all of the various functor types we talked about had this ability to compose. So we saw, for example, the ability to compose applicatives together. Right? We did this in week 3, or week 2 actually. We saw the ability to compose foldables together. And we saw the same thing with traversables. So if you remember traversables, the traverse type class was describing the set of type constructors that are both foldable, and they have a functor instance, and they defined that traverse abstract operation. So we saw that both list and option were both traversable, and hence we can compose those as well. But when we looked at the monad type class, I talked about how we were not able to compose monad instances together. Certainly we have a monad for both list and for option, but there is no compose method. There is no compose method directly on monad. You can see in this case what's happening here. When we tried to compose the list and option together, we got an applicative back. And really what's happening is that because we're using subtyping in Scala to model our type class hierarchy, monad extended from applicative, if you recall. So since we didn't override the compose method to have a more specific return type, to say like a monad plus a monad returns a monad, we're really just calling the applicative, the superclass's compose method, which is fine, but we're not actually getting monadic behavior here. We're just getting applicative behavior. So of course the problem here is like we cannot do something like a flat map call. So the preview I gave in the past of what we're going to talk about today is how we can, well, while we can't compose arbitrary monads together, a lot of specific monads like option or like list can be composed with another arbitrary monad to yield the fused behavior, the composite behavior. So this idea of taking like two different type class instances, or sorry, taking two different type constructors with their corresponding type class instances and fusing their effects together into some composite data type that has both effects, we're going to call transformers. The terminology does come from Haskell. In Haskell, they're known as monad transformers. I'm not going to call them monad transformers today because, as you'll see, we don't really limit their implementation to just monads. But they did start that way in Haskell. They are known as monad transformers in Haskell because of the way type class hierarchies are encoded in Haskell. They end up being typically being applicative just to monads. But in Scala, we can do things a little more generally than we can do in Haskell in this case. So let's exit out of the REPL here. And we'll start by writing something that lets us combine the option monad with another arbitrary monad. And remember, the idea here is that the option monad, like when we map, right, when we have an option we want to map over it, we get to write a map function that works on the inner type. And if our value is defined, of course, our function is applied to the value. And if our value is undefined, our function sort of skipped over, right? It's never used, and we just get back a none. So this idea of like optionality, like I get to work with things as if they always exist, and the option monad is going to track whether they do exist or not. That's what we want to be able to fuse, that optionality behavior or effect. We want to fuse it with some other arbitrary effect. So let's start here. We're going to create a data type called OptionT. And this is a pure data type, right? So we're not building a type class at this point. We're just creating a regular old data type. I am doing this in a brand new project. It's not in structures. We have a dependency on structures, so we can use all the things from it, all the type classes from it. But this is a separate project right now. And the way I want to start this is by wrapping a value of a particular shape. So we're going to have a case class here. I'll call it OptionT. And it's going to be parameterized by some type A. And the value we're going to wrap should have the shape f of option A. So we have this f in here, right? We want to abstract over like this arbitrary type constructor f. So we're going to have to make OptionT parameterized by f as well. So this is how we're going to start. We're going to say that the option T, where T stands for transformer, option T is always going to wrap an F of option A. So this could be a list of options, or it could be like a reader monad, which we'll look at in an upcoming week of an optional value. Any type constructor F here that you can put in, if it's an F of an option, that's what this type is going to wrap. So we'll start with that definition. That's our main definition of option T. Now what we can do is write various type class instances for option T, and we'll put those in the companion object. So the first we can do, let's just write a monad instance. Let's see how this goes. What we want to do is say that we have a monad for option T given F, and we need a question mark here. Because remember, monad abstracts over single argument type constructors. What we got here, of course, is a 2-argument type constructor where the first argument is a higher kind, or kind 1, and the second argument is kind 0. Monad, of course, we need to project this particular shape into a shape that's a type constructor of 1 kind 0 argument. So we can do that with this particular syntax, again, using the kind projector compiler plugin. The problem with what we've just written here is that we have used another type variable. We have type F. We haven't defined that, so we'll have to change our val to a def and take type F as an argument to our method. Okay, so let's save this, and we're going to start continuous compilation. Okay, so we've got a couple import errors. We'll fix those real quickly. Let's see what the next set are. All right, so far so good. The next set of errors are about the abstract methods on monad we haven't defined. So we can define these fairly easily. The first is pure. If you recall, pure has this signature that for some parameterized type A, we're going to get a value of it, and we need to return back this with A stuck in for the question mark. So we need to return back an option T, F comma A. So we'll come back to that in a second. The next one we need to do is the flat map operation. We'll just steal that from here. And then we'll clean up some of the imports. Whoops. Okay. So we need to fill out those two methods, but before we do, I want to take a close look at our definition of flat map. We're also going to run into a compilation problem because of this other error, so let's fix that real quick too. It's complaining because it wants simulacrum on the class path. So we'll just take these things from our structures build and put them directly into this transformers project. So here we're just adding simulacrum. And then we'll restart continuous compilation. So we should get green compilation at this point, if I did that right. Of course I didn't. Missing a comma here. And an extra comma there. Okay, so we should get green compilation at this point. There we go. And now we just have to fill in these two abstract operations. But first, let's look at the signature of flat map. So we start with an OptionT FA, right? Because that's the our type constructor with A substituted in for the question mark. And then remember, like flat map always has the signature A to F of B. And so we just do a blind replacement here where we say A to F. Remember, F is this thing, and we stick B in for the question mark. So what we have to return here is an OptionT instance. And then, of course, we need to return OptionT F of B here. Okay, so what I'm pointing out here is that we're not returning from flat map an F of option A, right? We're returning a specific OptionT FB. And I'll talk about that more in a few minutes. All right, well, let's do pure first because pure is pretty easy. We only have one way to construct an OptionT at this point, right? We have a case class. It's just a wrapper for this. So we can write OptionT. But now, this is just calling the apply method on the case class, right? But now here, we have to put an F of option A. Well, we could do sum A. That gives us an option A, but how do we get that inside of an F? And the only way we're going to be able to do this is by having a pure method for F. Like if we had some type class where we had a pure for F, we would be able to say, basically we'd be able to say this, right? Something like this, where we want to say, take this sum value and stick it inside of the F type constructor. Well, so we know a couple different type constructors that have a pure method, right? We know monad and we know applicative. And since we're not actually using flat map in this method, all we really need is applicative. So let's start just by requesting an applicative. So the way we're going to request that is just via an implicit constraint on this method here that we're defining. So we're going to add an implicit parameter block. We'll call it F. We'll add a parameter called F, and we'll make it of type applicative of F. Okay, so now because this F variable has type applicative of F, then this compiles fine. We can stick any value into the F type constructor. And then, of course, we can lift that into option, or wrap that with OptionT. So there's our pure definition. And you can see that compiles OK. Let's try flat map. So our input here is FA. It's an OptionT FA. And remember, we can always just say FA.value to get this thing out, an F of option A. So if we have an F of option A, we can use things we know about this type class F to get access to the value inside. So far, we've only required F is an applicative. So we could use, for example, apply, map 2, map 3, right? We could use just regular map from Functor because applicative extends Functor. And we're going to run into a bit of a wall. So I think we're going to need to strengthen this constraint on our F type constructor to require that it's actually a monad. Right? So every monad is an applicative. It just also has that flat map operation. So we're going to have a stronger constraint here. Given this stronger constraint, we could do something like f.flatmap. So we're going to flat map our value. And now what do we get here? If we have like an f of option A and we're flat mapping, here we have an opt A as a parameter. And what we're returning here just needs to be an f of some value, right? So we've got to, whatever we return from flat map, based off of the signature of this flat map here, the one on F, we know we're getting an option A as input. We can return anything we want as long as it's wrapped in the F type constructor. So we don't have to return an F option, for example, although in this case we're going to want to. So flat mapping on F, let's say we are going to return a, well, let me back up. We're flat mapping on F, so we know what we're getting back from now this overall expression is an F question mark. Whatever this guy is here, right? Whatever type this is, that's what we're getting back for this overall expression. But we need to return option TFB. So how can we go from an F question mark to an option TFB? Well, the apply method of option T is defined such that it can wrap any F of option A. So if we add a further constraint here to say, well, we're going to make this be the return here be an F of option question mark, then we can just wrap this whole response in option T, just using the regular option T apply method that we've already used. And now we even know what our question mark is, right? Because now our type constructors are aligned, but we know our output type needs to be B here. Therefore, we can work backwards and put B here. So this is getting a little more manageable, right? We know opt A is an option A, and we know we need to turn it into an F of option B. So what we're putting in for this question mark, this body here has to be an option A to F of option B. Okay, but we only have this, we have this function F we haven't even looked at yet, right? This function F requires just an A. So what are we going to do here? Well, basically we have a bunch of different options. We have this option A here. What we can do is let's start by trying to map over opt A. If we map over that, we get this value A here, and then we can call F of A. This overall expression is going to have kind of a funky type. It's going to be option of something, right? Because we started with an option A and we mapped, so the something here is going to be replaced by whatever the result of this is. And that is right here, so we'll just substitute that in, and we get this type. So that doesn't look like something that's very useful. And we notice that like if we unwrap this option T type, we can get back to this F of option A. Is there something we can do with that? Is there something we can do with an F of option A instead of just option here? So one way we could go about doing this, rather than working through and trying like flat map and keep trying different operations, is let's say pattern matching on our different values here. So let's say we pattern match on opt A. Of course, we've got our two cases that it's not defined or it's sum A. And now, overall, we still have to make both of these cases return an F of option B. Well, in the none case, we definitely don't have an A value to apply our function with, yet somehow we've got to turn it into an F of option B. So here we could just do f.pure none. That would give us an F of option B. In the sum case, we can apply our F function with A. So now remember, this gives us this option T FB. We want to get an F option B, and so in order to get that, we can just unwrap our type constructor. Our option T type here, remember, is just short for F option A. If you substitute B in for A, you get F option B, which is the exact output type we're looking for. So here, we can just put F of A dot value. if we did all of that right, that should compile fine. And now if we look at this, we can see that, like, well, all we're really doing is mapping f of a dot value over our option, and then falling back, if it's a none, falling back to f dot pure none. So maybe we would rewrite this to like op a dot map. And that would be our implementation of flat map. Okay, so I'm not going to define the a test for this particular monad definition that proves that it is law abiding, but it is. If you use the same kind of test infrastructure we were using when we were working in structures, and try to run the monad tests against monads generated from this method here, you will find that they do in fact pass the monad laws. And note that what I was saying earlier about how we're using a abstract operation here, or an abstract type constructor here. We're saying that you can generate a monad for any f, that you can merge the effects of any f type constructor with an option type constructor. And so, like, unless you actually have these type classes explicitly called out, right, then there's no way to even talk about a method like this one. Like, this method absolutely requires the monad type class in order to exist. So anyway, this is one way to do this. Is absolutely law abiding. So let's try to use it at the REPL and see some things that it enables. So we're going to open up the console here. And now let's do something, let's think. Let's say we've got x's, which will be a list of options. So basically the same x's that we started with earlier in the review. In order to, like, the operation we're going to use here is flat map, since that's the operation that we can't get by just composing, let's say, applicatives together. So we want to somehow compose the functionality of list with the functionality of option and use the flat map operation with that composed monad instance. So in order to do that, let's define a new type. We'll call it XS, or new value called XST, which will be OptionT list, comma, int. So you can see we're using the OptionT case class. We wrapped our list of options here. And now with that, we should be able to do xst.flatmap. This value coming in here, x, has type int, right? So just like when we composed two functors together and mapped a function over the composite, remember, like, even when we had a list of options, when we were mapping, we were dealing with just ints, right? We zoomed all the way into the type constructors, the nested type constructors, and got access to that inner value a. That same thing's happening here with flatmap, is that we're going to work on the individual ints. But now our flatmap operation has to return an OptionT FB, right? We see that up here. So the right-hand side of this flatmap needs to return an OptionT. The f, our f right here, up above on line 11, the return type of the function from flatmap, f is fixed, right? F is not part of the definition of flatmap here, right? F is part of its surrounding context. It's part of this monad definition up here. So because we've chosen to use flat map on our option T type, f has already been fixed to list. So we have to return an option T of list here. We can't substitute like another type constructor in. But B can be anything we want. So let's just say we, let's make it a string. Okay, so now in order to construct an option T list string, we're going to need here a list of option string. So we're turning an individual integer x into a list of option string. So maybe it's not a great motivating example, but we could do something like list.fill x with x.toString. So like the number 1 would become a singleton list with the string 1. The number 2 would become a 2-element list with the string 2, appearing twice, etc. Let's see, I think I have an extra paren there. Okay. So it's saying that that flat map's not a member of option T. And that's somewhat true. Certainly we didn't define flat map on option T, but we have defined a monad instance for it in the companion object, and our monad instance is available implicitly. So we should be picking up this monad instance here, and then via the enrichment methods, we should be getting flat map added to our data type. Unfortunately, we're running into an issue with limitations on Scala type inference as it relates to like figuring out different shapes. So we're going to have to fall back and rather than use the extension method, just call flat map directly on the type class. So it's a little less elegant, but it looks like this. We would say, give us the monad instance for option T list, question mark. So there's that monad instance. You can see it looked it up. And it returned, basically executed this line 9 here. In order to execute it, it needed a monad for f, but it found a monad of list, and so everything was OK. And now with that, we could call flat map, passing xst in, and then just taking the rest of our definition from above. Oh, of course, I screwed up the type. What it's complaining about here is saying that we're trying to pass a list of strings to option T, but we were supposed to have a list of option string. So the proper definition would look like this. So here we got flat map, and you can see the result was a list here. In fact, we can unwrap it. We'll just get our list back out of sum1, none, sum2, sum2. So you can see it turned, and these are strings, right? These aren't integers. So it turned our single value 1 into a single element list with the string 1 in it. It kept none as none. Then it turned 2 into a 2-element list of the string 2s. Right. If we had done the same thing with, let's say, 3, we'd have sum3, sum3, sum3 tacked onto the end here. So in the kind of the purest definition, this is how you would define the option T monad transformer. The idea is that we're able to generate a new monad from option plus some other arbitrary monad, and hence the name monad transformer. Now, admittedly, combining list and option together is not typically what you want to do. The problem is we haven't looked at very many monads yet that aren't collections. In fact, I think maybe the only monad we've looked at that's not a collection so far is like function. But in coming weeks we will see additional ones like reader or state or task or future, when you can start to combine these things in really interesting ways. And so, for example, if you have a monad for future, then substitute future in for f through all these examples, where here you have a future option A, and then you have some function that says, assuming that when the future completes, if it completes with a sum, flat map that into something else that generates a future option A. Use that value to compute the next computation in a set of asynchronous calls, for instance. So anyway, the option monad and the future monad complement each other very nicely, and the either monad that we're looking at, the either T monad that we're going to look at in a few minutes has the same benefit. Okay. The reason I want to call these transformers and not specifically monad transformers is that this was kind of painful to work with down at the REPL. This is completely legitimate. We need to have this monad instance in implicit scope so we can combine it with yet other monad transformers. But having to not or being limited such that we can't use extension methods is not very nice. Having to manually wrap things into OptionT is not very nice. So often you'll see various convenience methods added directly to the transformer type. So for example, maybe we want to say the map operation is very common, for this data type. So we want to define the map operation directly, here. Maybe same thing with flat map. Now we can't really change the data type here. We can't change the signature of these things. Map and flat map really should be the real map signature from Functor, and flat map should be the real flat map signature, from monad, which means we have to take a function from A to OptionT FB here, and we have to return an OptionT FB here. And of course, flat map here we can just lift directly. Right, we can steal our implementation from below. Our FA is just this, so we can get rid of the FA there. I think otherwise that looks okay. Oh, so this is kind of interesting. So the error we're getting is that f is not defined, that the value f is not defined, right? Our type f is defined up here, but here we are using f.flatmap. And remember down in our example down here, we did that because we have this implicit monad f. Notice over here we're using f.pure, right? So we've got two uses of f. We have the monad type class that abstracts over the ability to have pure and flat map, but we've got no implicit instance here. So we have a couple different options. We could put it here. This is sort of the obvious place to put it. What else did we get wrong? Let's make sure we get it compiling before we refactor that. Oh. Okay. Oh, and since we moved this implementation up, by the way, we can change our flatmap definition down here now, just to call fa.flatmap. And that'll compile fine. Okay, so we can put this definition up here, but it turns out that's actually a little too constraining for Scala, right? Or this is let me rephrase that. This is sort of the Haskell way to do it. That we're going to capture our type class instance here. We're going to capture it directly as part of our data type, and then we have it available to all of these methods. But there's a couple different ways we can come at this and realize that there's a better way to do it, a couple different angles we can come from. One is that we're exposing this monad implementation to all of the methods inside of this data type. And when you think about it, that's a bit of a violation of our parametricity principle, right? When we talked about parametricity a few weeks ago, it was all about taking the bare minimum needed in any given operation, the bare minimum constraints needed in order to implement that operation. And so, for example, our map operation here does not need a monad instance for f. Let's write our map operation and see what we actually need. So for this one, we have we have an f of option A. We've got our function from A to B. So really all we need is the ability to map over f. Right? So if we map over our value, then what we get here is an opt A. We need to return then an opt B, and we can do that very easily by saying opt A map f. If we do that, what we're getting as a result here is an f of option B, so we're going to wrap the whole thing in an option T. All right, so there's our map definition. And this compiled fine because we're going to pick up map from our monad up here. But since all we're using is map, we really only need a functor for f here. So this definition of defining our implicit constraint on our f-type constructor at the class level ends up being a violation of parametricity. We're exposing that f's a monad to the map function, despite the fact that the map function does not need to know that information. Furthermore, like if we wanted to combine option with any other type constructor, f, such that f's not a monad, but it does have a functor, we lose the ability to do so using this syntax. So instead, we can move this constraint down into these individual methods. So we can say flat map only exists if you can provide evidence that f is a monad, but map can exist if you can provide evidence that f is a functor. And now this is sort of the best of both worlds. Now if our f type is not a monad, we can still use option T to wrap an f of option A, and we can still use the map operation, as long as f's a functor. We've somewhat altered the shape of our method here, but that's okay because even though, like for instance, flat map and map now have this extra implicit parameter block, their pure type class instances down here, or like their regular type class instances down here, have not been impacted at all, because the type class instance, we capture that entry here. And notice we don't have any other option down here. Like down on line 16, we cannot physically push monad f, this type constraint, down into each one of these operations, because it's going to say, flat map. I mean, really, it's going to give you an error saying that you define some extra flat map operation with a different signature, and that's fine, but you didn't implement this abstract flat map operation that has this signature. Right? And of course, like if we wanted to be parametric in our type class instances as well, then perhaps what we should be doing here is defining a functor here. Without pure, something like that. Another advantage of this particular encoding is that we can define convenience methods on option T that have even, who have signatures that depart even further from our normal type class signatures. Oops. So for example, Scala Z defines something called flatmap F. And it's really, it's nothing more than a convenience. It just says that often when working with an option T, you're going to want a flat map, but where your return type is just an F option A. I'm sorry, F option B. But otherwise, the rest of this is going to be the same. And so, of course, flat map F can be written in terms of flat map. Here all we're doing is saying take the F option B and wrap it in the option T type constructor. We could further reduce that to just option T dot apply. Let's try one or two others. Let's do. We'll come to. We'll look at some of these another day for either T. But let's do a couple other methods on option T. We can think of option T as sort of like a fancy kind of option. I mean, really, it's just this, right? It's an F of option A, but we can reach through the F type constructor and provide option-like methods directly on option T. So two option-like methods. We have isDefined, which typically on option returns a Boolean, but we can't do that. We can't get rid of that F, but we can return an F of Boolean. And the other one is, we could define is empty, which could also return an F of Boolean. I said we can't get rid of the F because, at least with what we have so far, because we have no way to abstract over the ability to extract values from a type constructor. Our value is an F option A, so we can get at the value inside the type constructor and manipulate it while it's still in that context F, but we have no way to pull it back out, at least at this point in time. We will see a way to pull things back out generically in a few weeks, but for now we don't have any way to do that. So here for isDefined, really all we need to do is just map over our value and call the isDefined method on option. But in order to map, we need a constraint on F, right? We're going to need the fact that F is a functor. And then isEmpty is we can't just define as like not isDefined, right? Even though that's really what it is, we can't do that because we need, our isDefined returns an F of Boolean. So we've got two options. We could say it's the result of mapping over isDefined, and then just map, not over that Boolean. In order to do that, we're going to need an implicit F functor instance. Or of course we could define this in terms of options isEmpty method, in which case it would look like the same thing as isDefined looks, right? It's just map over the value and call that isEmpty. Either result's the same. And so we can continue to add these types of convenience operations with the general intuition that it's going to be an operation that works off of an option, or looks like it works off of an option, but we're going to have the result wrapped in the F-type constructor. One operation that's very useful in option is get or else. Get or else is typically defined like this, right? Like when you call it on option A, you say get or else, and you pass in some default value for the case where it's none. So we're going to say here, we can return you an F of A. We can basically dissolve the option out of the type constructor. Just get rid of it. And this is, sort of an obvious implementation when you think about it, right? We're going to map over our f type constructor. We've got some option here. Oh, sorry. We're going to map over the value. We've got some option here now. And then we'll just call get or else on that. Now, of course, to map over this type constructor, this is going to need a functor. So with some of these additional convenience methods, let's try to put these to the use and see what we get. So we had the x's example earlier. So given our definition here, we could wrap x's in option t. Then we could say xst.get or else, and let's say 42. And now notice what we did. We converted each sum in the list to just its value, and we converted each none in the list to the value 42. We got back a list, of course, because list was our type constructor. And so I think this is an interesting case because I think when you look at get or else here, it's just pure boilerplate with the way we're forwarding the method through and just mapping over our value. But when you combine it with an arbitrary type constructor, you get back some novel results, I think. And of course, doing this over futures would mean, like, a future option calling get on else, you get back a future defaulted value. You'd be able to turn like a future option int and just into a future int, just with a call to get or else. Let's just use one of the other ones. We'll do like is defined, let's say. Oops. And here we get a list where all the sums get turned into trues and all the nones get turned into falses. So that's pretty much what I want to cover this week. It's interesting when you go back now and look at our option T type, though, that the only two methods that required a monad were flatmap and our convenience function for flatmap. These other three methods, map, is defined as empty, and get or else, all just required a functor. And we could do things like define, we could do things like define an apply function that is in spirit the same as like the applicative apply function, yet just has an additional implicit constraint on it. And return like an option T f of b as a result. In which case, that also would not require a monad. And doing so is actually a really interesting exercise because there are two ways to define this apply operation. So like the full operation will look something like this. So hold on, let me think. We're going to do def apply like that. That's the general idea. But there are two different ways to implement this on option T. that take different implicit constraints here. And they're both valid, like they're both useful functions. They both can't be called apply. I'll give you a hint. One of these could be written such that the constraint on F is that it's a monad, and the other one can be written such that the constraint on F is that it's an applicative, and they're implemented differently and at times could come back with different results. So anyway, you can't define them both, so you could have like, maybe you would define these as like apply M for monadically and apply A for applicatively. But this is a pretty good exercise if you want to try filling it out. Any questions for this week? Looks like there's at least one. It says, is the functor transformer different from compose, like functor.compose? No. So in this case, this functor definition down here is, well, so yes and no. Functionally, it's no different. Meaning that taking, like, let's say in this case we were dealing with a list of options, right? That's what OptionT is going to abstract over, like a list of options or a future option or whatever. So the net effect of taking like a list of options, wrapping it into OptionT, using the functor definition we have, and then unwrapping it when we're done, would be equivalent to just using the functor for F composed with the functor for option. So from that perspective, no, they're not any different. But in our encoding of this stuff, like the way we're representing these abstractions in Scala, the big difference is that option T is a different data type from F of option A. So if anyone ever has an option T and they want a functor instance for it, they're not going to be able to get it. So there's still a benefit to defining this functor instance down here, but we could have implemented it like this instead, right? Rather than implementing functor manually here, we could have implemented it as functor F compose functor option, and then just squash the bugs that the compiler would start producing. Right? The compiler's going to have bugs here, of course, because the input and output of this is F of option, and yet we need option T. So on the way into everything, we'd have to lift things into option T, and on the way out, we'd have to unwrap them back out to F of option, whatever. But functionally, they're the same. Any other questions? All right, well, that's all we have for this week.